Hey, stop, man. Hey, Lit.
So you want to see?
Yes. I tried to call you twice and I haven't heard your voice.
I did hear when you close to me. But have you called me twice?
Yeah, I tried to call you twice.
Okay.
You are not hearing your voice.
Okay. Do you know why I was unable to hear you when you were far from me?
Honestly, I have no clue.
Okay. Let me tell you. So when I was close to you, the sound intensity was decayed what I was able to hear. But when you were far from me, the sound intensity has been completely decayed. I was unable to hear you. So do you know how can we model this using mathematics? This is what this can be captured through logarithmic function.
Interesting. I want to know more about the logarithm series or a log application of log. Can you explain me a bit more so that I can understand more about log? What is it? Where it is coming in?
Fantastic. That curious we should never die. Let's have a look.
So, logarithmic functions are mathematical functions that are inverse of an exponential function. They represent the relationship between the input variable and the exponent needed to obtain a specific value. The logarithmic functions have the general form f of x equal to log base x, where b is the base of the logarithm. Now, let's discuss the inverse of an exponential function. Logarithmic function and exponential functions are closely related and they serve as inverses of each other. If y equal to b power x, then x equal to log base of y. Logarithmic function helps us to find the exponent required to obtain a specific value given a base. So one of the most important examples of logarithmic functions are signal processing. So logarithmic functions play a crucial role in signal processing and frequency analysis. So logarithmic scales such as the decibel scale are used to measure and represent the magnitude of intensity of the signals. Logarithmic function help analyze signal power, amplitude and frequency relationships. So in decibels, the intensity of the sound is measured in a unit called decibels, right? So which describes the relative intensity of a sound based on a logarithmic scale containing values ranging from 0 to 194. The intensity of a sound reaching a person's ear depends not only on the intensity of the sound produced but also on the person's distance from the source of the sound. If you were standing on 1 foot away from the loud machine, for instance, you would experience higher decibels. If you were 10 feet away, even though the intensity of the sound produced remains unchanged.
Excellent, senior. Brilliantly summarized the whole logarithmic function. You gave the mathematical interpretation of logarithmic function. But one more thing, I just want to add one more point to that. So just to make the clear-cut distinction and the relation between exponentiation function or exponential function and logarithmic function. So to put it in a simple way, when you see an equation y is equal to b power x or b to the power x, we can say that y is the exponentiation of b. The equation represents the exponential function where b is the base and x is the exponent. By raising the base b to the power of x, we obtain the value of y. In other words, y represents the result of exponentiating the base b by the exponent of x. You have to see with respect to the function in the prism of function. So now this is exponentiation function. Now let's get into the logarithmic function. If you have to write the same equation in logarithmic equation, you have to write in x is equal to log base b of y. So we can say that x is the inverse exponentiation of b. So the equation represents the logarithmic function, where b is the base and y is the value for which we are finding the logarithm. So by taking the logarithm of y with respect to the base b, we obtain the value of x. In other words, x represents the exponent to which we need to raise the base b in order to obtain the value y. So hence we can interpret x as the inverse exponentiation with base b. Sum it up. Y is exponentiation function and x is inverse exponentiation of b. So to the day in day out application of logarithmic function in a data scientist life. So obviously the most important step in data science process is, as you know, it's pre-processing, feature engineering or EDA, so data cleaning. So out of that, the most important one when it comes to feature scaling. So the logarithmic scaling is applied to features in some machine learning models by taking the logarithm of feature values. Skewed distributions can be transformed into more symmetric forms. So this can help improve model performance, particularly when dealing with features that have a wide range or follow a power law distribution. The second application is probability and information theory. So logarithmic functions play a crucial role in probability theory and information theory, so which are foundational to machine learning. So logarithmic functions are used to calculate logarithmic probabilities, information entropy and information gain. The very important thing, information gain, which is again used in feature engineering. Information gain is a feature selection algorithm, my friend. So they enable quantification and manipulation of probabilistic and informational quantities in various machine learning algorithms. Obviously, you all know your loss function. Logarithmic functions are employed in calculation of loss functions in machine learning. For example, the binary cross entropy loss function uses logarithmic functions to measure discrepancy between the predicted values and actual values in binary classification problems.
That was fantastic, Lead. That was really very well put. I will add some more points on top of it. So model evaluation. Logarithmic functions are used in evaluating the performance of machine learning models. For instance, the logarithmic loss or log loss metric is commonly employed to assess the accuracy of the probabilistic predictions. Log loss penalizes the model based on the logarithm of the predicted probabilities. So it is well calibrated and confident predictions. So in rank ordering, logarithmic functions can be utilized in rank ordering of items or recommendations. By taking the logarithm of certain metrics such as click-through rate or user ratings, the value can be transformed to a logarithmic scale, which obviously gives a better representations. So the next one is regularizations. So a logarithmic function can be applied in regularization techniques to control the complexity of the machine learning models and to prevent overfitting. For example, in L1 and L2 regression or lasso regression or regularization, the logarithmic function is used to induce sparsity by penalizing the absolute values of the model coefficients. Well, in collaborative filtering, logarithmic functions find application in collaborative filtering as well. So they are used in recommendation engines, and they help address the problem of popularity bias by applying logarithmic scaling to item ratings or user interactions, making recommendations more balanced or diverse.